Hello everyone, welcome to EEE 137. This is week number 7, problem number 2, the statistics of the random telegraph process. So consider a random process x of t that assumes the values positive 1 or negative 1. Suppose that x of 0, take note that this is our initial condition, is equal to positive 1, or x of 0, the initial condition is negative 1 with equal probability. And suppose that x of t changes polarity with each occurrence of an event in a Poisson process of rate alpha. Okay? So we want to determine the mean function of the random process and also its autocorrelation. So how do we do that? Let us first consider a sample realization of this random process. So this is time and this is our realization of the random process. So the initial condition once again can be positive 1 or negative 1 with equal probability. So for example, we start at positive 1 and then there are certain polarity changes for each occurrence of a Poisson process. So Poisson process will be discussed in the following week. Okay, but just think about the Poisson process as an arrival at a certain time. Okay? Just think about an arrival of something at a certain time that is defined by alpha, the rate alpha, and is defined by an exponential random variable. Okay? So there's an arrival here, okay? And then there is another arrival here. That arrival, that inter-arrival time is described by a exponential random variable. That will be discussed in the next chapters of this course. Okay? So another arrival after some time, okay, and then another arrival here, and that arrival is defined by a parameter alpha. Okay, so that is a sample. This is just a sample realization, and once again, this realization will vary depending on the nature of the random process. Okay, and then so this is 1 and negative 1. Recall that at each specific time instant, we have here a random variable. Okay? A random variable defined by x of t1. Okay? For example, this time here is t1. We have here a random variable at time t1 defined by x of t1. Okay? So now we want to determine if we can get the mean function. So we can just get the distribution of x of t1, and since we have a Poisson process, therefore this x of t1 is assumed to not change across time. Okay, since the Poisson process has a constant arrival rate alpha, right? So we can just assume that x of t1 is the same across time. Okay, and we need to determine this x of t1. Okay, the probability mass function. Probability mass function because we only have discrete values here, positive 1 and negative 1. So we want to get the probability mass function of x of t1. Specifically, we want to get probability of x of t. Okay, where x of t is either positive 1 or negative 1. We want to get probability of x of t is equal to positive 1 and probability of x of t is equal to negative 1. And since we have only two outcomes here, then we should follow this certain rule that probability of x of t is equal to positive 1 must be equal to 1 minus probability of x of t is equal to negative 1. So this expression must follow because when we add the two probabilities together, they make up equal to 1. That is just the consequence of the axiom of probability. So you could just review that. So we can choose which one we should compute or which one we should solve. So for example, we want to solve probability that the outcome x of t is equal to positive 1. Okay? So this is equal to, okay, you could use the total probability theorem because we have two possible outcomes here. Either the initial condition is positive 1 or the initial condition is negative 1. So we could use the total probability theorem. So we could get probability of x of t is equal to positive 1 given x of the initial condition is positive 1. That means at time t, the outcome is the same as the initial condition multiplied by the probability of the initial condition being equal to positive 1. And then we add that, again, this is total probability theorem, right? We add that to the probability that x of t is equal to minus 1, given that the initial condition is minus 1, multiplied by probability the initial condition is equal to minus 1. So take note here that these quantities, we already know the computation for those probabilities because it was stated here that the initial condition has equal probabilities, right? So if they are equal, they are only two outcomes. Therefore, the probabilities are equal to 1/2. They are both equal to 1/2. Okay? So we only need to solve these two quantities. Okay? So for instance, when we have probability x of t plus 1 given x of 0 is equal to plus 1. So for example, this is x of t. Okay? For example, this is time t. What is the probability that when we start at positive 1, we would end at positive 1 also at time t? Okay? So that is the probability of that happening is when, okay, take note that we have certain number of transitions. So, for example, this is the first transition, this is the second transition, this is the third transition, fourth, and then this one is the sixth transition. Therefore, for us to have the same value with the initial condition, we must have 6 transitions. Or more generally, we want to have an even number of transitions. Okay? Or even number of success or even number of arrival times in our Poisson process. Okay? So this one, we can solve this by getting, okay, let me just write that. This is equal to the probability of even number of transitions or even number of success in the Poisson process. So we could use the Poisson random variable here because we have here a constant time interval and then we are trying to obtain the probability of the number of success during that time interval. And we must get all the possible even number of transitions to get this value, So we multiply that by probability x of 0 is equal to positive 1. Okay, how about the second one? How about the second term? If you want to get the probability that x of t is positive 1 given x of 0 is negative 1, then we are trying to get an odd number of transitions here. Because when we start here, okay, when you start here, we must obtain an odd number of transitions for us to jump to the opposite polarity or opposite outcome, right? So, the second term is odd number of transitions multiplied by the probability of x of 0 is minus 1. And we know this to be 1/2 once again. So we are just concerned with these two problems or probabilities. Okay? So recall the Poisson random variable once again. So the Poisson random variable is defined as probability of k, where k is the number of success over time interval, let's say t or tau. This is equal to e raised to negative alpha tau times alpha tau raised to k over k factorial, where k here is the number of success in that Poisson random variable, and alpha is the arrival rate, tau, okay, is the time interval that we have over that Poisson process. So just over that Poisson random variable. So just review that random variable. Okay. So what we are trying to get here is we want to get all the possible outcomes that have an even number of success, k. So we obtain summation from k is 0 to infinity of e raised to negative alpha tau times alpha tau raised to 2k over 2k factorial. Take note that 2k just means that we have an even number of success here. Because when we substitute 0 here, 0, and then 1 here, we have 2, 0, 2, 4, 6, 8, 10, right? And then we multiply that by times 1/2. Okay? And then we add here the odd number of transition. E raised to negative alpha tau times alpha tau. If we want to get the odd number of success, we can just add 1 here. 2k plus 1. 2k plus 1 factorial multiplied by 1/2. So this is the probability of x of t is equal to positive 1. So we have to just solve these quantities, right? So we use a certain mathematical expression when we have summation from k is 0 to infinity of z to the 2k over 2k factorial. We have here a hyperbolic cosine of z. On the other hand, if we have z to the 2k plus 1 over 2k factorial, we have hyperbolic sine of z. So we can use this property to simplify this one. Okay? So just take note that this property only applies to this, right? And then we bring out e to the negative alpha tau outside. Since we are only summing over k, the variable k. So, simplifying further, we will now obtain 1/2 e raised to negative alpha tau times, this is even number of transition, therefore this is equal to hyperbolic cosine of alpha tau, right? Plus 1/2 e to the negative alpha tau. This is hyperbolic sine of alpha tau. Okay? And then we just simplify it further. 1/2 e to the negative alpha tau hyperbolic cosine alpha tau plus hyperbolic sine of alpha tau. Recall that when we have a hyperbolic cosine, we can express it as sum of exponentials. So we have, just recall your math, we have e to the alpha tau plus e raised to negative alpha tau over 2 plus e to the alpha tau minus e raised to negative alpha tau over 2. So we will have a cancellation here. We will obtain 1/2 e to the negative alpha tau times e raised to alpha tau, and this is equal to 1/2. Once again, this is the probability x of t is equal to positive 1. Okay? So, to get the other outcome, which is probability of x of t is equal to negative 1, well, you could repeat the process of doing that, but we know from axioms of probability that this is equal to 1 minus probability x of t is equal to negative 1. Therefore, we have probability x of t is equal to minus 1 is just also equal to 1/2. So they have actually equal probabilities. Okay? We just proved that they must have also an equal probability of happening. Okay? And we've gone through some rigorous math process just to arrive at this kind of answer. Okay? And if you want to get the expectation of that or the mean function, we can get 1 times probability x of t is equal to 1 plus negative 1 times probability x of t is equal to minus 1. This is equal to 0. So this is now our mean function, okay, for our random telegraph signal. Okay, so that means when we have this random process, okay, when we get the random variable here, we will obtain an expected value that is equal to 0. Okay, so that's how you solve this, the mean function of this random telegraph signal. Okay, how about the autocorrelation? So for the autocorrelation, this is equal to, okay, expectation of x of t1 multiplied by x of t2. Okay, take note that when we take the product of 2, take note that x of t1 and x of t2 will only have two possible outcomes, so positive 1 or negative 1. And also that the product, okay, the product of the two will also have two possible values only, positive 1 or negative 1. When is this product equal to positive 1? When, okay, take note, when the two outcomes here is similar. So it's either positive 1 times positive 1 or negative 1 times negative 1. They have similar signs. On the other hand, we will obtain negative 1 for our product if we have different signs. Okay? So, let me just draw that once again. Okay? We have here our random process. For example, we take two time instance here, t sub 2 separated by, let's just say, tau. Okay? We would obtain the product of these two random variables, or these two outcomes, will be equal to positive 1 if we have similar. So let me just write that. Expectation of x of t1, x of t2 is equal to, okay, the outcome is positive 1 when we have x of t1 is equal to x of t2. Okay, we want to get the probability of that. On the other hand, we will obtain negative 1 if we have probability x of t1 is not equal to x of t2. That is the case when over this two time instance, we have different values. Okay, because positive 1 times negative 1 is negative 1. On the other hand, negative 1 times positive 1 is negative 1. And actually, we've already obtained this, right? When we have time interval tau, for us to obtain similar value given an initial value to the next value, we have that the probability of that happening is equal to an even probability of even number of transitions. And we already solved that, right? And that is also the case for negative 1. We must have odd number of transitions. So this is equal to, okay, positive 1 times, what is the probability of even number of transition once again? E raised to negative alpha tau hyperbolic cosine of alpha tau plus e to the negative alpha tau hyperbolic sine alpha tau. So now, e to the negative alpha tau cos minus sinh of alpha tau. And we have e to the alpha tau plus e to the negative alpha tau over 2 minus e to the alpha tau minus e to the negative alpha tau over 2. Right? So simplifying, we have e to the negative alpha tau times, okay, so this one will cancel, and then we will have e to the negative alpha tau, right? So this is equal to e raised to negative 2 alpha tau, okay, or e raised to negative 2 alpha absolute value t2 minus t1, okay, Rx of t1 t2 is equal to, so that is our autocorrelation function, right? So that's how you solve this problem. See you on the next video.